Hello everyone, welcome back to the next part on the structural equation modeling. In this part of the lecture we will learn what are the path coefficients in the SEM, and for this we will recall what we know already about the variances, covariances, correlation and regression coefficients. Also we will learn how to calculate direct and indirect effects and where we get the unexplained variances by our model. Indeed, we will have some repetition, what you have already might know, especially in the part about variance and covariances. But as I know from the previous course that many students like to have such a repetition in order to be able to follow the material. First, let's use our example that we used for our exercise on grassland project. And here I show two path diagrams which we have reproduced. And the first diagram uses the unstandardized path coefficients which are shown here in red in our summary table for this our model. And the second path diagram shows the standardized coefficients which are shown in blue here. So our path coefficients, they show the relationship among our variables in the model. And also in this specific model, this relationship are causal. So they are directed from one variable to another variable. And as you might guess already, the building blocks of these path coefficients are variances of our variables in the model, the covariances among these variables, the correlations, and the regression coefficients. First, let's recall what we know about the variance. So let's say we have variable x, which has 6 data points, and these are our sample size. And each data point is spread around the mean, which is shown by red line. So the difference between data point and the mean are called residual. And the variance is the sum of all residuals squared divided per sample size minus 1. And in R, for our variable, we can find the variance using function varx. And if we have two variables, let's say x and y, then we can measure the dependency between them, which is called covariance. And covariance is calculated as the sum of the product between the residuals of the first variable and the second variable, divided per sample size minus 1. In R, we can use function co to calculate the covariance between the variables. Here I show the covariance matrix between the variables x and y, and as you might know already that the on diagonal value shows the variances of each variable, and the off diagonal value shows the covariances among two variables. So you can see here that the covariance equals 6.66, and it's quite difficult to interpret what does it mean, what this value mean. And this is because we have totally different scales of x and y here. And the covariance is scaled to the raw values of these variables. If we check the mean, we can see that mean of our y is much more higher than mean of x, and that's why the variances of y is much more higher than variance of x. So in order to understand the degree of dependency between these two variables, we need to put our x and our y on a common scale. The common way to standardize the variables is to adjust their means to zeros and their variances to 1. And the simplest way to bring the common scale for the covariance is to standardize it on the standard deviation. And this is what our correlation coefficient does. It takes the covariance between two variables and standardize it per the product of the standard deviation of the both variables. And as you remember, the standard deviation is the square root of the variance. And the correlation matrix, which is shown here, now has the variances which are equal to 1 because they are adjusted to 1, and the covariance is brought to the common scale, which is from 0 to 1. And now when we have this common range, we can know what is the meaning of this covariance here. So we know that this is 0.14, and if we we think that it can vary from 0 to 1, that we can say that it's quite low. And to get the correlation in R, we simply can use the function core for both of our variables. And here I also show the hand calculation so that you know what is the formula behind this core function. But in case if we know the direction of the relationship between the variables, so we know which one is the predictor and which one is the response, then we rather look for the regression coefficient than for the correlation. And the regression equation is shown here, where y is predicted by x. So here our data points of y are not compared to the sample mean of y, but are compared to the predicted mean. And this predicted mean are predicted by our x variable. And the a coefficient is the intercept. This is the value of our y when x equals 0. And the regression coefficient b is the slope of this predicted mean. And now our difference between each data point to this predicted mean are our residuals. And then b coefficient, which shows the strength of the effect of x on y, is calculated as the covariance between these two variables scaled to the variance of the predictor. And then if we want to standardize our b coefficient, then we can relate it to the correlation coefficient via the standard deviation of each of these variables. If in the structural equation model we have two variables connected by a single link, like shown here, then the path coefficient for this link is equal to the correlation between these two variables. But if the variable in our model is connected by more than one link, then our path coefficient for these links are the partial regression coefficients. And here is an example how the path coefficient specifically for this link is calculated. And the idea behind this partial regression coefficient is that now we have here the effect of x1 on y2 coming from two different sources. So this is this direct link and also indirect through y1. And in order to get the independent effect of x1 on y2, we need to remove the shared variance between x1 and y1. So we have to remove this part of the effect here. And this is what is done by this formula here. It removes the joint influence of x1 on y1 and y1 on y2 in order to get the independent effect of x1 on y2. But this formula is a standardized partial path coefficient. As you see, the correlations are used here. And to get the unstandardized coefficient, we can multiply this coefficient per the quotient of the response standard deviation to the predictor standard deviation. So now let's take our example in the Lavaan in R. For this, we have data, txt file named SEM data1. And first step is to specify our model. And given that we have only regressions here, so to express them, we use single tilde, as you might remember. And then I want to fit the model using our data and to extract the results. Specifically, I want to have the standardized coefficients. That's why I showed here that these are true. And the summary function gives us the results for the regression coefficients, and these are our path coefficients. And the estimates in red are the unstandardized, and in blue, all are our standardized path coefficients. Then, depending on our study, we choose which one we take and fill our path diagram. And here an additional thing, what I did, I made the link from x1 to y2 in gray in order to show that this effect is not statistically significant here. The form of the representation of past coefficients, I mean unstandardized or standardized, depend on the aim of our project. So we can choose the one or another based on the goals. So if we want to predict the raw units of the changes in our system, then we can use the unstandardized past coefficients. Also, it has a direct real-world meaning in case if you want to know how much change in absolute unit of one variable is caused by a 1 unit change in the other variable. And if our models have the variables that are identical units, then we can, of course, use the unstandardized past coefficients. But in many ecological studies, the majority of them display the standardized form of past coefficients because even they have less clear real-world meaning, the idea usually is to compare the strength of the effect across different links, across the variables with a different scale. And this also would allow to compare links not only in one model, but also in different models with the variables of a different scale. And next, let's talk about the indirect effects in the SEM. For this, we will use our previous example. And in this model, the effect of x1 on y2 is not only direct, as shown by this blue link, but also indirect, mediated by our variable y1. That's why we can call it mediator. And in the example, we see that the direct link equals minus 0.1. And the question is how to calculate then these indirect effects. And the indirect effect is a product of the coefficients realized through the mediator. So it's a B2 coefficient multiplied per B3. And then the total effect is the sum of direct and indirect effects. And here is a calculation for our example where we calculated direct, indirect, and the total effects. We don't have to calculate direct, indirect, and total effects by hand, but we can ask Lavaan to do this for us automatically. So for this, we will have to define these effects in Lavaan. But the first step would be to label our parameters. And as you can see here, I have added the labels for the coefficients for each variable. But note, these parameter labels should start with the letter, not with the number. Now, when we label the parameters, we can define the direct, indirect, and total effects. To define them, we have to use the colon together with the equal sign. And this means in Lavaan the definition of some parameter. And as you can see here, I define the direct effect is our B1 coefficient, indirect effect is a product of B2 and B3, and total effect is the sum of direct indirect. When we have this direct and indirect defined here, instead of this line, we can simply use total equal direct plus indirect. And then, of course, I refit my model using data and ask summary. And now the output table will also give us results for our defined parameters, which are our direct, indirect, and total effect. And if we compare them to our hand calculations, you can see that they are totally equal. And now one more important thing that, as you remember, if our variable in structural equation model has more than 2 links, then these past coefficients are partial. And then if we have total effect, which includes direct and indirect effects, this is equal to the total correlation between x1 and y2. And now when we have basic understanding of past coefficients in the SEM, we can talk about the unexplained variances by our models. Here I recall again our previous example, and I would like to remind that in the SEM, the predictor variables are called exogenous and the response variable are called endogenous. And as you remember from the previous slide, the total effect of x1 on y2 is equal 0.44. But this means that the x1 cannot 100% explain the variance in our y2 variable. And if it would explain 100%, then this total effect would be equal to 1. This means that there are some other sources or that explain the variance in our endogenous variable. And you might be more familiar with this diagram where the unexplained variances are our residuals, the deviations of our data points from the predicted line. So we should include the error variances also to our equation form in addition to the predictors. And in the past diagram, the residual variances are shown by the circles and the arrows pointing into our endogenous variables. This means that there are unknown sources which predict our endogenous variables. The error variances can be calculated as 1 minus r square, and r square is the variance of the variable explained by the model. To get the r square, we can use the argument r square equal true in our summary function. And here you can see the output, and here are the r square estimates for each of our variables. And now I fill this r square for each of variable in our path diagram. But we don't have to calculate our error variances by hand. We can obtain them automatically from our summary function. For this, we have to look into the part of the table called variances, and it gives us unstandardized estimates and standardized estimates for these error variances, which I have already filled here in these circles. One another thing is the link from error variances to our variables. And this link shows the influence on our variables from unmodeled factors. And if we want to know this influence, we have to search for this coefficient for this link. And it can be calculated as the square root of our variances, and it's known as error effect or error correlation. And using this formula, I have calculated these path coefficients for the correlation between error variance and our variables. And now when we look on this result, for instance, on our variable y2, we can say that our model explains the 52% of variance in y2, and there are other sources that are not modeled here, which explain around 48% of variance in our y2. And the effect of these unmodeled sources is quite high, it equals to 0.69. Here I summarize the major points to remember from this part of the lecture today. I will not go through the details, but I suggest you take time and think through each of these points. And now this is time for your task. You know the project already, we used it to do our first exercises, and it is on the effect of grazing on plant diversity along elevation gradient. And the data are on Blackboard named grassland data CSV file. And here you can see the conceptual model which we produced in our first exercises, and the path coefficients here are standardized. So for your exercises on this task, please use all the standardized coefficients. And here are the final tasks. So for this model, you need to calculate the direct, indirect, and total effects of grazing on diversity. You need to do this in R. Of course, you can do this by hand as well in order to check your results from Lavaan. Second, you need to define the exogenous and endogenous variables in this model. And then for each endogenous variable, get the following measures: the variance explained by the model for each variable, the error variance, and the effect of the error. So these are the path coefficients with the error variances. And in the next part of the lecture today, we will talk about the covariance-based SEM, and this is a big part of our course, and understanding of covariances and correlations is a basis for understanding the procedure of covariance-based SEM. So see you soon on the next lecture, and also see you during the seminars.